So welcome to this video on creating your own functions. So functions are sort of the bread and butter and the workhorse of R. They're a way of applying operations and transformations to objects or data to achieve an output that allows us to make sense of our data or to transform or to plot our data. A lot of the functions that come pre-packaged either with base R or in a lot of the packages that you can install and download will achieve the effects or the result that you want, whether it's applying linear regression models or plotting your data. But often it's useful to be able to write your own functions. Because R is open source, it's contributed to by the community. There are no closed doors, so all of the functions that you see, or many of the functions that you will use and will see written, have just been written by academics, members of the community, because you can just quite simply write your own function, quality control them, produce good documentation for them, wrap them up, and then package them so that other people can use them. And whether you choose to do that or whether you just write functions within your own code for your own convenience, it's not a difficult thing to do at all. And once you start using functions, it will stop you from having to copy and paste your code and to apply reasonably complex operations to perhaps large data sets quite quickly. Before we start, I recommend that you've already watched and completed the Conditional Statements and Loops video that I produced, because we'll use some of the concepts that we talked about in that video in this one. So just a quick recap on some sort of built-in functions that you may already have used in R, and also a reminder that you can save the output of functions to variable names. So let's use the rnorm function to generate 1,000 values from a random normal distribution of mean 0 and 1, and we'll call this normal distribution, normal dist. And then we can use the mean function on normal dist and get a mean value. Remember that this will be different to what you get because of the random nature of this function. We can use the hist function to plot a histogram of our data. And if we're not sure or want to read more documentation on how a function works, we can type question mark, the name of the function, and we get some information on how to use the function in the help pane. Now, usefully, we get this information about usage for the function, and we get a list of all the arguments that you can supply to the function. Now remember that if an argument doesn't have a value specified with an equal sign, then it is a mandatory argument that you have to supply as a user. And if an argument has a default value supplied with equal signs, then you don't have to supply it. The function will use whatever the default value is, or you can supply an argument to it if you wish to change the default. So, for example, we can change the breaks argument and supply our own. So we can say hist normal dist breaks equals 50. Control enter, and then we see that we have a histogram with a larger number of interval breaks. Remember also that you can supply arguments to functions either by position. So this x, we could have said x equals normal dist, but because x is first, and often for functions that take a data argument, the first argument is the data, we don't need to. We didn't actually need even to supply this breaks argument. But common wisdom says that apart from data arguments, it's good practice to name the arguments that you're supplying for the ease of interpretability. So let's write our first function. So functions don't have to take arguments. So they can just return a value whenever they're called, regardless of receiving no input. So the way to write a function is that you write whatever you want the function's name to be. And it's important that the name of a function tells you concisely exactly what the function is going to do. So our function is going to be called say hello. And again, just like you're assigning an object, you use the assignment operator, and then you use the function. If your function takes arguments, you supply them inside the curly brackets. Ours doesn't, so we're going to leave them blank, which basically tells we're creating a function that needs no arguments. And then you open curly brackets, and then general convention is to start the body of the function on a new line, and you can see that RStudio has put the closing brackets on a separate line, and then we put the body of the code between these two curly brackets. And so we're writing a function that just says hello. And so we hit Control and Enter, and now we've saved this function to say hello. And if you want to call it, if we try and just call say hello as if we'd written an object, we get the body of our code as we've written it. If we actually want to be able to use say hello as the function itself, we need to remember to use the brackets at the end, which tells R that we are writing a function. And if we call Control and Enter, then R prints out hello. But let's change this so that our function takes an argument. So let's copy and paste this. And let's say that we want the function to take one argument called name, and change this so that it uses the paste function. So remember, the paste function pastes together character strings or different values separated by a comma. So hello, and then the name variable. So it will paste together hello, and then whatever we supply as the name argument. So if we do Control Enter to update the function, and then we're going to save the output of the function call to an object called greet. And then we're going to call say hello, and then I'm going to give my name, which is Hirvin. You can give your own name if you want. Hit Control Enter, and then if we call the greet object, our function has returned hello Hirvin. So that's an example of a function with no arguments. We've had an example of a function with one mandatory argument. Sometimes you want to create a function which has default values, which you are able to change if you so wish. And so we can create an object that has both mandatory and optional arguments. So we're going to create an object which just returns the value of a number that we give it to the power of some exponent. So we're going to call our function expo for exponent. Not the best name of the function in the world, but it is fine for now. Function. And then our data argument, which is mandatory, is going to be x. And then we're going to have a second argument, which is an optional argument called power. And the way that you tell R that this is an optional argument is by giving it a default value. And the default value is going to be 2. And then we open curly brackets and then put the body of our function between these. And then actually we're going to get our function to return histogram of x to the power of our power argument. And then define the function and try running it with no arguments. And we can see that we get an error saying error in hist to the x to the power of power. The argument x is missing with no default because we didn't give the function call a default value. So if instead we give our vector of values normal dist that we defined earlier, we get a histogram of every value of normal dist to the power of the default value of the power argument, which is 2. I could change this, and instead we could define this as 3. And so I'm using positional matching to tell it that I want power to be equal to 3, but I could type power equals 3 and run this again. And then this time we get a histogram of all the values in norm dist to the power of 3 because I've specified this power argument. Now notice that our functions can use functions inside them, which is perfectly fine. That's no problem at all. Sometimes we want to be able to supply arguments to these internal functions which actually don't really have any bearing on the rest of the function or the main functionality of the function. And we can do this using unnamed arguments. So remember earlier we supplied this optional argument to the hist function for the number of breaks. Well, let's say that we want to be able to do that inside this function. All we do is, if we just copy this for the time being and paste, you'll see in the documentation for different functions often these 3 dots, this ellipsis. And this means basically any other arguments that are relevant. And this is how we supply unnamed arguments to our function. So we're not going to change much to our function, but instead we're going to add an additional argument at the end here, which is just ... which means any additional argument. And then we're going to add these this ellipsis as an argument to the histogram function. And basically what this means is, after the user has supplied the x argument, and after the user has supplied the power equal to 2 argument, or not if we've used it as the default value, any additional arguments that are supplied to the expo function are given to the internal hist function. And so we can do something like, let's actually run this, we can do something like expo normal dist power equals 1 breaks equals 50. And so the x argument has been handled by our function call and has been given to hist here. The power function has been handled and has been given here. The breaks function has been sort of categorized as being any other function and was passed directly into the histogram function here. So that's a way of controlling or supplying optional arguments to functions that are within your main function. Now we can also define arguments which are logical. So for example, we might want an argument which is either true or false. And depending on the value of this argument, the function will do one thing or the other. So for example, let's redefine our expo function. Takes data argument x. This time we're going to call the exponent exp. This by default is going to be 2, and then we're going to have a hist argument which by default is equal to false, and then we're going to allow for any other argument there as well at the end. So inside our function we're going to wrap an if statement. So we're basically going to say that if the hist argument is equal to true, plot hist of x to the power of exp and allow for any other arguments. If hist is not true, then we're going to pass it to the else function, which will just return x to the power of exp. And what I forgot to do actually is just underneath the histogram function, we're going to return this value as well. So basically what will happen is, by default, this hist argument is false. So this evaluates to false, and this code is not run, but instead this is run. So if hist is equal to false, the function will return the values of x to the power of exp. If hist is true, the function will plot the histogram of the data and return the values of x to the power of exp. So we define the function, and then we can call our function on normal dist. So with the default values, it returns every value in our our random distribution to the power of 2. And if we supply the hist equals true argument, then we get the values returned again, but we also get the histogram plotted on the right hand side. So this is a way of using logical arguments, true or false arguments, to control the functionality of our functions. So let's try a motivating example. So I've always found that the definition of passages for suspension cell lines to be a little bit arbitrary, and instead counting the number of times that a population of cells doubles its number is a slightly more meaningful way of tracking population growth and the longevity of your cells. And so we're going to define a function which takes the starting number of cells and the current number of cells and reports the number of times that the population has doubled between those two counts. So what I mean by population doubling is that if we start with 10,000 cells and next time you count them you have 20,000 cells, the population has doubled once. If you start with 10,000 cells and count them today and you've got 40,000 cells, you've had 2 population doubles. It doubled once to 20,000 and then doubled again to 40,000. And so we're going to write a short function which allows us to, which does this calculation for us. I'm going to write out the function and then we'll look back at it step by step to explain exactly what it's doing. So we're going to call this pop double, nice meaningful name, function, and it's going to take 2 arguments, start, which is the starting number of cells, and end, which is the end number of cells. And both of these are going to be mandatory arguments with no optional arguments. So we're going to define an object called doubling, which is going to start with the value of -1. And then we're going to use a while statement inside our function. So while end is larger than start, increment doubling by 1, and double start. And then outside of the while loop, we want to return doubling plus end divided by start. Okay, so let's initialize the function and let's have a think about what's going on. So let's say that start is 10,000 and end is 20,000. So the function initializes an object called doubling, which starts to be at -1. And then we go straight to the while loop. So while end is larger than start. So remember, for example, this is 20,000 and this is 10,000 for our example. Increment doubling by 1. So doubling is now equal to 0. And then start is now doubled. So start now becomes 20,000. We've come to the end of the while loop, so we go back to the top. And end is 20,000 and start is now 20,000 because we updated it on this line. So this evaluates to false. And so we go straight to the very end, which is doubling, which is 0, plus end divided by start. Because end is 20,000 and start is 20,000, this is equal to 1. And so this is 0 plus 1. And so if we run our function, we see that we've had a single population double. If we do the same thing for 40,000, we see that we've had 2 population doubles. If we do 3,000, we can see that we've had 1.75 population doubles. So let's walk through it with the 30,000 cell case. So doubling starts off at -1. End is 30,000, start is 10,000. This is true. So doubling becomes 0 and start becomes 20,000. And we go back to the while loop again. End is 30,000. Start is now 20,000, which evaluates to true. And so doubling is increased by 1 again. So doubling now becomes 1. And start is doubled. So start is now 40,000. We go back to the while loop. End is 30,000. Start is 40,000. So this evaluates to false. And so we go down here where doubling is 1 plus 30,000 divided by 40,000. So this is 1 plus 0.75. Now, once we've defined our function, it's important to test it with a range of different values to make sure that it gives you the output that you would expect it to. And so in this case, it might include feeding lots of different values to the function to make sure that it gives you the results that you expect. And so, for example, if yesterday we counted 10,000 and then today we counted 100,000, then our population has doubled 3.625 times. So I hope that was a useful introduction on writing your own functions in R. Hadley Wickham, who is a very famous contributor to R code, famously says that when to define a function is basically if you find yourself copy and pasting something 3 times, write a function that does it for you instead. And when you start off, you may find that taking the time to think about how to code and write your own functions might take a bit more time than actually if you just copied and pasted your code your code and done things over and over again. But actually, the more practice you get at doing it, the more time you save in writing your own functions, and the more succinct your code becomes, more easily readable, and the more that you can adapt and use your code for different situations, especially when you start writing functions that take lots of different optional arguments that allow you to fine-tune exactly what the output is.